partial pressure of atmospheric oxygen suddenly doubling from 20.9% to 42%. We usually treat oxygen as a purely life-giving substance. Because aerobic organisms require it to survive, it is easy to assume that doubling the supply would provide a massive metabolic upgrade. The physical reality of gases dictates otherwise. If we hold the nitrogen and argon in our atmosphere constant, adding that much diatomic oxygen directly increases the total mass of the atmosphere, pushing the surface pressure from a standard 1 bar to 1.21 bar. That added mass alters the global radiative budget. The atmosphere is forced into a trade-off between the cooling effect of Rayleigh scattering and a severe warming effect caused by the pressure broadening of greenhouse gas absorption lines. This shift guarantees 3 cascading consequences. First, global hypercombustion, mass vertebrate extinction, and rapid arthropod gigantism. A simple volumetric increase in a single gas shatters the chemical equilibrium that allows Earth's current biomes to exist. At our modern 20.9% oxygen level, fire propagation operates inside a narrow window. Ignition is strictly gated by fuel moisture. Wet wood does not burn easily, providing a natural constraint on the size and frequency of wildfires. This chart from the hyper-ox model visualizes the relationship between oxygen concentration and burn probability. Our 20.9% baseline sits right on the edge of a steep incline. As the oxygen variable pushes past the 30% critical threshold and approaches 42%, the burn probability curve skyrockets vertically. At this extreme partial pressure, the activation energy required to sustain an exothermic oxidation reaction drops completely out of the equation. Routine geological and meteorological events become apocalyptic ignition sources. A single lightning strike or rock fall provides all the heat needed to start a fire that cannot be easily extinguished. High fuel moisture in tropical zones currently serves as Earth's natural fire break. At 42% oxygen, water content in vegetation no longer suppresses fire propagation. The firestorm ignores seasonal dry cycles. It consumes the wet, complete incineration and loss of up to 86% of all terrestrial biomass. Forest cover is restricted to highly isolated, high-latitude refugia. At 42% concentration, the atmosphere acts as a universal solvent. It prioritizes combustion over biological preservation. While the flora burns, the hyperoxic environment selects a very specific survivor: terrestrial arthropods. Insects do not have lungs. Their respiratory morphology relies on passive gas diffusion, drawing air through a network of hollow tubes called trachea that penetrate their tissues. This scaling curve shows the rigid mathematical constraint governing their size. Tracheal volume scales hypermetrically. For every unit of body mass an insect gains, its respiratory system must expand by a factor of 1.29. At our current 21% oxygen baseline, this scaling law creates a strict physical bottleneck. The insect's exoskeleton, particularly at the leg orifices, limits how much space the trachea can occupy. If the insect grows too large, it literally runs out of room for its respiratory system and suffocates. This structural conflict places an absolute biological cap on modern insects. The largest living species max out around 17 centimeters in length. When we inject the 42% oxygen variable into this model, the doubled partial pressure gradient forces a radical physiological reconfiguration. Through a process known as phenotypic plasticity, insects adapt to the dense oxygen by developing much thinner, highly efficient trachea. They require less internal space to transport the same amount of gas. Removing that internal spatial constraint triggers a morphological release. The insects scale up, driven by the hyperoxic atmosphere, to undergo an evolutionary gigantism identical to the ancient Carboniferous period, expanding into predators with multi-foot wingspans. It is oxygen diffusion limits, rather than genetics or vertebrate predation, that form the invisible cage currently keeping the insect kingdom small. As the insects thrive, mammalian biology completely collapses in the 1.21 bar environment. For mammals, chronic hyperoxemia is a severe, systemic cellular toxin. The toxicity is driven by the aggressive overproduction of reactive oxygen species, or ROS, generated inside the mitochondrial enzymes. This molecular model illustrates the exact target of that toxicity. Deep inside critical DNA repair and energy generation proteins, there is a delicate iron-sulfur cluster. The excess ROS molecules directly attack and chemically oxidize these clusters. Stripped of its iron-sulfur core, the protein sequence suffers total structural failure. It unwinds and deactivates. This biochemical oxidation is a literal, rapid rusting of the organism's fundamental cellular machinery. The macroscopic symptoms of this rusting appear swiftly. Tissues undergo permanent cell cycle arrest and premature senescence. The alveoli in the lungs hyalinize, and the central nervous system rapidly degrades into acute seizures. For complex vertebrates, high-pressure oxygen ceases to act as life support and functions purely as an inescapable corrosive poison. The 42% simulation yields a very clear biome, a high-pressure, globally deforested incubator dominated entirely by hyperscaled arthropods and completely devoid of mammalian life. Oxygen itself is an aggressive, volatile oxidizer. Its capacity to destroy life is just as potent as its capacity to sustain it. Pulling the atmospheric variables back down to the modern 20.9% baseline restores to physical constraints required for our current biosphere. Earth has maintained this exact percentage for 55 million years through a strict regulatory network of photorespiration, wildfire feedbacks, and the carbon cycle. Our 20.9% oxygen level sits exactly on a razor's edge. It is precisely calibrated to be just high enough to prevent biological suffocation and just low enough to prevent planetary incineration.